Hi viewers, in this class I will discuss another important mode of heat transfer, that is radiation. As all of you are aware, radiation does not require a material medium for the transfer of heat. In fact, perfect vacuum is ideal for radiation heat transfer. Also, all bodies above absolute zero temperature in the universe emit as well as receive radiations. The radiations emitted depend on the temperature. Today, I will discuss some of the theoretical aspects related to radiation heat transfer. There are two theories proposed to explain the radiation heat transfer. They are Maxwell's theory and Max Planck's theory. According to Maxwell's theory, the energy transfer is taking place as a result of radiations emitted from a body due to changes in electronic configurations of atoms or molecules. The electromagnetic waves so produced travel through space and strike another body and transfer energy. They travel with speed equal to the velocity of light. Max Planck's theory. Max Planck proposed photons as the carriers of energy. According to him, thermal radiations is taking place in the form of discrete quanta or photons. When these photons strike another body in its path, energy is transferred. Thermal radiations. All bodies in the universe above absolute zero temperature emit radiations and receive radiations. So all bodies in the universe is emitting radiations because all the bodies are above absolute zero temperature. Any body if you take, it is emitting as well as receiving radiations. Now radiations which are in the wavelength range of 0.1 to 100 micrometer range is only produce appreciable heating effect, and they are called as thermal radiations. So all electromagnetic radiations will not produce heating effect. Only part of electromagnetic spectrum in the wavelength range 0.1 to 100 micrometer range are only producing some appreciable heating effect. So they are called thermal radiation. Radiosity and radiation. Now radiations will be striking on the surface, and the total radiation falling on a surface or striking on a surface is known as the radiation, and its unit is watts per meter square. So radiation is the total radiation falling on a surface, and out of this total radiation falling on a surface, part may be reflected, part may be absorbed, and part may be transmitted. So let us consider the reflected part. Reflected part is there. One part is reflected from the surface, and all the bodies above absolute zero temperature will emit radiations. So all bodies will be emitting radiation, and the surface may be reflecting a part of the radiation which is directly falling on the surface, and that depends on the surface property and the radiation falling on the surface. So from the surface there will be always emitted part of radiations, and maybe you will have a reflected part of radiation. The combined total reflected part of radiations plus emitted part of radiations is known as radiosity. So radiosity is the total radiation leaving a surface, whereas radiation is the total energy falling on a surface. So its unit is watts per meter square, the rate of energy falling on a surface per meter square area. And this is radiosity is the total energy leaving a surface per unit area per unit time. Now out of the total energy striking on a surface, that is irradiation, a part will be reflected, part may be absorbed, part may be transmitted. Let us say the irradiation is G. Now let us represent reflected part as GR and absorbed part as GA and transmitted part as GT. So out of the total irradiation, GR is the reflected part, GA is the absorbed part, and GT is the transmitted part. Now the fraction of energy reflected, that is GR by G, is known as reflectivity. GR, the part of 100 watts per meter square is if it is falling on the surface. If 20 watts is per meter square is reflected, then 20 by 100, that will give the reflectivity, or 0.2 will be the reflectivity. Out of 100 watts per meter square striking on the surface, if 20 watts per meter square is reflected, 20 by 100, that will give the reflectivity. So reflectivity is the fraction of energy reflected from the surface. Similarly, absorptivity, which is the fraction of energy absorbed, that will be GA by G. Suppose out of the 100 watts per meter square striking on the surface, if 70 watts is absorbed, its absorptivity is going to be 70 by 100 or 0.7. Now, out of 100 watts per meter square, 20 watts is reflected, 70 watts is absorbed, the remaining is 10 watts per meter square. So 10 watts per meter square is transmitted. So that is GT is 10 watts per meter square. GT by G, that is a fraction of energy transmitted, will give the transmissivity, or it is 0.1 in this case. So transmissivity is the fraction of energy transmitted. So we have three terms. One is absorptivity, that is a fraction of energy absorbed, and another one is reflectivity, which is a fraction of energy reflected, and lastly we have transmissivity, which is a fraction of energy transmitted. The summation of all this absorbed energy plus reflected energy plus transmitted energy will give the total energy falling on the surface, that is the radiation. So radiation is equal to summation of the absorbed energy plus reflected energy part and transmitted energy part. Now if you divide the equation, that is this equation which I have written here, if you divide by G, Ga by G is fraction of energy absorbed, which is absorptivity, and Gr by G, it is a fraction of energy reflected, which is reflectivity, and Gt by G is a fraction of energy transmitted, and it is transmissivity. And we get the right hand side, G by G will give 1. So that means absorptivity plus reflectivity plus transmissivity, the summation will be equal to 1. So in the previous example, absorptivity was 0.7, reflectivity was 0.2, and transmissivity was 0.1. So all the summation of the fraction of energy absorbed, reflected, and transmitted, summation will be equal to 1. Opaque surface. An opaque surface is one which does not transmit any of the incident radiations through it. So in that case, the transmissivity is 0. So no part of the radiations is transmitted. Transmissivity is 0. So we have alpha plus rho plus tau is equal to 1. Tau is 0. So we'll get alpha plus rho is equal to 1. Maybe some part of the radiations may be absorbed, or some part of the radiations may be reflected, but no part of the radiation is transmitted through it. Such a surface is called opaque surface. And most of metals are opaque in nature, and they do not transmit any of the incident radiation through it. Let us see which surface can be called as a black body. A black body is one which absorbs all the incident radiations falling on it. All the incident radiation, that is the radiation falling on the surface, is absorbed. No part of energy is reflected, no part is transmitted. All the energy totally, if 100 watts per meter square is falling on the surface, even 100 watts per meter square is absorbed. Per meter square area, if 100 watts is falling, completely it's absorbed. No part is transmitted, no part is reflected. In that case, alpha is equal to 1. A body which absorbs all the incident radiation on it is known as black body. Surfaces coated with the black paint or black color usually to have absorptivity nearly 1, but no bodies are perfectly black, and some of the even bright surfaces will act as a black body. They absorb incident radiation. So color is not the only criteria to decide whether the body is black. Now some of the bright surfaces, some of the bodies which are bright in color like snow, will absorb most part of the radiations falling on it, and they behave like a black body even though they are bright in color. But most of the black colored surfaces absorbs most part of the radiations falling on it. So most of the surfaces which are black in color will behave like a black body, nearly black body, but no bodies are perfectly black and absorbs 100% of radiation falling on it. We can idealize a black body by creating a spherical cavity like this with a narrow opening in it, and inside surface of the cavity is coated with the black paint. In this spherical cavity, so the inside portion is coated with the black paint, which has absorptivity nearly equal to 1. Now any of the incident radiation coming into the spherical cavity through this narrow opening, after striking, most part of that radiations will be absorbed by this black surface. Let us say that absorptivity is 90% or 0.9. Absorptivity is 0.9. So if 10 watts of radiations is coming inside, then 90% of that is 9 watts will be absorbed, 1 watt will be reflected from it. and no part will be transmitted, assuming that is an opaque surface. So 9 watts is absorbed, 1 watt is reflected, and after again striking on the this surface which is coated with the black, again 90% is absorbed, only 10% is reflected. So 90% of 1 watt is 0.9 watts, and 0.1 watt is reflected from here. Again, after repeated reflections on this surface, before leaving the spherical cavity, most part of the radiations will be absorbed, and only a small portion of the incoming radiations will be leaving the spherical cavity. So this spherical cavity can be idealized as a black surface. Now let us see what is a white body. A white body is which reflects all the incident radiation on it. So all the incident radiation falling on it, if it's reflects, then you can call it as a white body. Highly polished surface will behave like a white body. For white body, transmissivity is 0, absorptivity is 0, and all the incident radiation is reflected. So reflectivity is equal to 1. A highly polished surface will behave like a white body. Now we will see what is the total emissive power. So it is the total radiation energy emitted from a surface in all hemispherical direction per unit area, per unit time is known as emissive power and is denoted by E. So emissive power, the total emissive power is the total radiation emitted from the surface in all directions. So in the hemispherical directions, so it can be in the perpendicular, or it can be inclined 30 degree from the normal or 60 degree from the normal. So in all hemispherical directions, in whichever directions possible, the energy emitted per unit time, per unit area is known as emissive power of a body, and it's denoted by E. And all the bodies in the universe will emit radiations. The emitted radiations will be maximum for a black body. So black body will emit maximum radiations, and the emissive power of a black body will be maximum, and it can be denoted by EB. So if two surfaces, so both are at same temperature, out of which one is a black surface and another one is a real surface, the black surface will emit maximum radiations compared to the real surface. Real surface, always the emissive power will be less than that of a black surface. So black bodies will emit maximum radiations from its surface, and the emissive power, the unit is watts per meter square. That is energy radiated per unit time per unit area. So it is the total energy emitted from the surface per unit area per unit time. So that is emissive power. Stefan Boltzmann law. It is a basic law governing the radiation heat transfer. It is defined for a black body. It says that for a black body, the radiation emitted from its surface per unit area per unit time is proportional to the 4th power of absolute temperature. So it's for a black body. Emissive power of a black body is denoted by EB. It is proportional to 4th power of absolute temperature. Absolute temperature. So it should be in Kelvin. The temperature should be in Kelvin. The total emissive power of a black body is proportional to 4th power of absolute temperature. EB is total radiation emitted by a surface per unit time per unit area for a black body. It's proportional to 4th power of absolute temperature. If temperature is more radiations leave the surface. So it is proportional to 4th power of absolute temperature. Now the proportionality constant is sigma. So you can write EB is equal to sigma T to the power of 4. Our sigma is known as Stefan Boltzmann constant, and its value is 5.669 into 10 raised to minus 8 watts per meter square Kelvin to the power of 4. So this is a Stefan Boltzmann constant, and you can find out the total radiation emitted by a surface per unit area per unit time. That is the total emissive power of a black body. This is applicable only for black bodies, and that is equal to sigma T to the power of 4. So if you know the temperature of a surface, if it's a black surface, and if you know the temperature, you can find out the total energy emitted from the surface. Thank you for watching.